Every task executed by a massive language model relies on microscopic math. The basic building block of this system is the artificial neuron. To process information, a neuron requires an input called a vector. A vector is an ordered list of numbers representing real-world properties. In a housing model, square footage, the number of bedrooms, and a zip code are encoded into a vertical stack of numerical features. This process translates physical variables into the structured mathematical format a model needs to begin work. Inside the neuron, each vector feature is multiplied by a weight, determining its mathematical importance. These values combine into a single weighted sum. Finally, the neuron applies a bias, shifting the threshold to fire even with small inputs. Weights and biases provide the mechanical levers a network uses to determine which pieces of data are relevant to a specific goal. A neuron calculating only weighted sums is limited to linear math. This type of calculation can only map straight-line relationships, which cannot capture the volatility of real-world data. The solution is the activation function. This graph shows how functions like Sigmoid or ReLU take linear inputs and squish them into nonlinear curves. The activation function compresses the raw weighted sum into a standardized range, typically between 0 and 1. This final value serves as a trigger, determining if the neuron's signal is strong enough to be passed on to the next layer in the network. Without these nonlinear triggers, multiple layers of neurons would mathematically collapse into a single, flat, linear model. The activation function prevents this collapse, creating the depth necessary to learn complex real-world variables. In a full layer of a neural network, the single input vector enters dozens of parallel fibers simultaneously. Because every neuron in that layer has its own unique configuration of weights and biases, each one reacts differently to the same incoming data. Through training, these neurons specialize. One might fire only when detecting large suburban floor plans, while another responds strictly to high-density zip codes. The model's ability to recognize patterns is an emergent property of these specialized neurons firing together across the entire layer. Stacking billions of these specialized neurons creates a multi-layered neural network capable of processing massive datasets. The Anven AI architecture utilizes this scale, orchestrating 3 billion parameters, each one a specific weight or bias tuned for enterprise tasks. Expanding the parameter count to 3 billion allows the network to learn the statistical relationships between disparate weight types, like words and pixels. This density of weights and biases enables the model to generalize across new edge cases, providing the framework for multimodal reasoning. Billions of individual weighted sums and activations operate in parallel to produce the final output of an enterprise model. Running 3 billion parameter calculations simultaneously typically requires massive cloud computing infrastructure. Treecapital bypasses this hardware requirement through quantization. This chart demonstrates how compressing mathematical weights from standard formats to 4-bit sizes creates a 75% reduction in memory footprint. This compression lowers power consumption and memory overhead while maintaining accuracy levels comparable to non-quantized models. As shown on the right side of this framework, these efficiency gains allow Anven to run locally on mobile devices or private air-gapped servers without a network dependency. By mastering and shrinking the math of the individual neuron, Treecapital AI delivers secure, sovereign intelligence directly to the enterprise edge.